All right, welcome to the Explainer. Today, we're doing something really cool. We are going to walk the assembly line of a next-generation AI agent. And just to be clear, we aren't talking about your basic run-of-the-mill chatbots anymore. We're cracking open the actual blueprint of 2026's most advanced frameworks. We're going to piece together exactly how a fully autonomous system thinks, remembers, sees, and ultimately, how it proves its worth in a real-world production environment. Here's the roadmap for this Explainer. We've got 5 sections to cover: the Agentic AI upgrade, building the agent brain, mastering AI agent memory, giving agents visual perception, and evaluating agent performance. Section 1. The Agentic AI upgrade. Okay, let's dive right into this massive paradigm shift we've been seeing. We have officially moved away from simple, static bots to robust, autonomous systems that can actually drive their own workflows. The contrast between where we were and where we are now is frankly startling. Traditional RAG is incredibly rigid, kind of like a one-off extraction step. You ask a question, it fetches a document in a single pass using a static control flow, and, well, you get what you get. But agentic retrieval, it's a completely dynamic operation. It's iterative. It isn't just a pre-processing step anymore, it's a fluid, adaptable process that's entirely controlled by the large language model itself. So if the first search doesn't yield the right answer, the system is actually smart enough to pivot mid-process. The crucial takeaway here is that the agent is literally in the driver's seat. Agentic retrieval means the agent decides when to retrieve data, what specific queries to run, and exactly which tools or external sources to use. And most importantly, it decides whether the results are actually sufficient to answer the prompt. It iterates, it reformulates its approach continuously until it hits a specific stopping condition with enough concrete evidence. Section 2. Building the agent brain. Let's move to our next step on the assembly line and see how this all builds into the core reasoning engine. Because obviously, an agent that can retrieve data still needs a brain to process it, right? To understand this brain, we can look at LangGraph logic, which maps out the agent's decision-making loop sequentially. It starts by generating the initial query and retrieving documents, but here is where the autonomous reasoning really kicks in. Step 3. It actually grades those documents. It basically asks itself, are these relevant? If they pass the grade, it jumps ahead to step 5 and generates an answer. But if they fail, it routes to step 4, actively rewriting the question to try again. It's this continuous, dynamic loop of reasoning, acting, and observing. But we do have to remember the inherent risk in multi-step reasoning. Because the agent is making a series of changed decisions, failures compound. If the agent makes a flawed retrieval in step 2, like, say, it pulls an irrelevant document, that bad data shapes its reasoning in step 5, which could inherently corrupt a tool call it makes way down the line in step 8. Without tracing this full chain, you might just see a bad output, but the originating decision that caused the whole mess remains hidden. Section 3. Mastering AI agent memory. Now, equipping our agent with a reasoning brain is only half the battle. If it can't remember context from one turn to the next, it's pretty much useless. I absolutely love this quote from Fountain City because it hits the nail on the head regarding modern AI development. The context window is RAM. Confusing the working memory of the context window with long-term storage is exactly why simple agents perform amazingly well in a quick demo, but completely fall apart after a few months in production. When you flood the context window with stale facts and bloated history, the agent just loses focus. So to fix this degradation, we have to build what we call a Goldilocks memory layer. This means feeding the prompt exactly the volume of memories the agent can use for a specific turn. No more, no less. Everything else? That requires a dedicated retrieval call. By keeping the working memory strictly focused on what the agent needs right in this exact moment, we ensure it stays accurate and sharp, even as its history accumulates over time. Section 4. Giving agents visual perception. Okay, now that our agent can think sequentially and remember efficiently, let's upgrade its perception so it can process complex, real-world documents just like a human would. The difference here is absolutely staggering when you're dealing with multimodal content. Like, imagine a textbook full of charts and equations. Traditional RAG attempts to strip away vital visual layout just to extract plain text, which completely destroys the structural context. But vision language models, like Cole-Poly, represent a massive leap forward. They process the raw page holistically. They aren't just extracting text, they're looking at the page exactly as it is, preserving the spatial layout and the critical relationship between diagrams and the text surrounding them. So, how does it actually pull this off? 1024.
Call Poly achieves this incredible visual understanding by dividing every single document page into 1,024 manageable 32 by 32 image patches. Each of these patches is then converted into a rich embedding that seamlessly captures both the visual data and the contextual data. So when the agent searches, it's calculating similarity scores against these visual patches, entirely bypassing that flawed text extraction phase we used to rely on. So, look at what we've done. We've pieced together the ultimate 2026 AI agent. It's got agentic retrieval, a multi-step reasoning loop, a Goldilocks memory layer, and visual perception. But after building this absolute beast of an autonomous system, we have to ask the ultimate reality check question before we even think about deploying it. How do you actually know it works in production?
Section 5, Evaluating Agent Performance. This is where things get serious. Running diagnostics is absolutely essential to prevent catastrophic mistakes, which brings us to Databricks and the rigorous mandatory phase of evaluating agent performance. There are several highly relatable headaches for any developer building autonomous systems. Because agents operate dynamically, tiny logic errors cascade. You might see an agent confidently invent an API tool that literally doesn't exist. That's a hallucinated tool call. Or perhaps it gets stuck in an infinite loop, continuously retrying the exact same action and burning through your compute tokens without making any progress at all. Or it commits to dead-end reasoning early on and simply cannot recover. To diagnose and fix these really complex issues, Databricks emphasizes that you cannot rely on just one type of testing. You need both. Component-level evaluation is all about isolating specific functions, like testing just the retrieval quality or just the router. But end-to-end evaluation assesses the holistic workflow, measuring whether the final output is safe, accurate, and cost-efficient. You have to trace the entire span of reasoning using LLM judges and rigorous deterministic scoring to truly understand how your agent is behaving under the hood. I want to leave you with a final, somewhat provocative thought. Dominating generic public leaderboards is completely meaningless if your agent fails when it encounters your proprietary enterprise data. Standardized tests simply don't reflect your unique schemas, your internal tools, or your specific safety constraints. So as you move from prototyping to a fully autonomous production system, you have to ask yourself, are you relying on vanity metrics, or are you truly ready to build custom benchmarks that guarantee actual production reliability?